Yes, we are live. Venkat.
No. Let me share my screen here. Yeah, I just shared the simulator I found online. So I thought that would be a good place to start. How many of you have seen some version of this in some undergrad course, Pendulum on a Card?
I did, yeah. Like same as you a long time ago.
All right. So we'll walk through some of the like background later, but this is the basic setup. Um, this is schematic. In this case, it shows a four-wheel vehicle with the uh, pendulum on a loose hinge. It's not an actuated hinge. And what you can measure is the horizontal position X and the angle of the pendulum. So let's see, let's reset this. And yeah, these are the gains I last had it at. But look what happens. So basically, it's like balancing a broomstick on your hand, and you don't get to control the angle, so you're not gripping it. So you just have to move it. So I posted the link in the chat as well as in Discord. So pull it up and play around with this a little while. And the key thing to look at is this equation here. It's basic. So this controls both position and angle. You can also do just the angle. Uh, if you do just the angle, this is a PID controller, as you may know. So the first parameter is the proportional gain on the angles. So that's the first term, Kp theta times theta, so minus sign. The next one is the integral term, and the last one is the derivative term, so velocity or angle rate. And usually you don't add the integral unless there's like some steady disturbance or something. So start by playing around with proportional and derivative for a bit, then switch to control the position as well. And here the guy has set it up so that you have proportional and derivative control on the angle, and your proportional integral and derivative control on the position. And the reason he's added integral is uh, once you get the pendulum balanced, you may be far off from the horizontal position you want to be in. And then you want to kind of slowly bring it back to the position you want to be in. And the general intuition here is that the pendulum is a much faster time constant. So it's kind of the fast inner loop, and the horizontal translation is the slower outer loop. So you typically want to put higher gains on the angle and lower gains on the card, something like that. So that's the basic intuition. It's been a long time since I did one of these sims. All right, let's take 5 minutes, pull up the simulation and play with it and try to get some intuition for how it works.
So it's supposed to balance on
Yeah, it's
by the
supposed to
parameters.
balance, and I would be shocked if any of you got it even remotely close to balancing, because it's not a trivial problem. But you'll get some intuition of the how the dynamics of the system behaves, and you'll see later why it's not a trivial problem at all. Let me run the random simulation. And you can increase the simulation length. It's set to default at 5 seconds.
Why do you have 5 gains? I have only 3.
Check the box that says control position. So when page loads up, I think it's set to do only the angle.
Does it get any feedback from the position?
Yes, it's doing both position and angle. If you look at the equation, that's basically the force on the cart. It's a function of like the position and derivative of the angle, plus the position integral and derivative of the position.
Okay.
Let's give it another minute.
What happens if we invent a perpetual motion machine?
Use it as a screensaver.
Yeah, I think the way he set up the simulation, there's no damping or friction in it. So yeah, you can get into basically perpetual motion in this version, I think. All right, let's stop. Any immediate thoughts on the 5 minutes of playing? What did you guys try?
I have no intuition for it. That's what I learned. I'm missing some theory.
Yeah.
Oh.
Anybody else?
There is a. I remember I had to tune some sort of PID controller for one of the satellite models in my courses, and there is like a step-by-step way to get closer and closer, but I have forgotten it. So first you adjust like one of the gains, and then you go to the next one.
Yeah, that's called gain scheduling. It's one of the techniques you can use in systems like this. Though your satellite is actually harder because it's 3D and it's like much more non-linear. So
yeah, so like in the course we had a floating ball, so it was like restricted to one axis.
Yeah,
and then you had a reaction wheel inside, so yeah, basically controlling.
It's still harder than the inverted pendulum. Yeah, the usual laboratory version of that is ball on a cart. So there's like a seesaw type thing, and then there's a ball rolling on it, and then you control the seesaw and make the ball not roll off the seesaw. So that's the simplest version of that.
For us, the ball was pneumatically lifted, so you had a cup in which the air was blown, and then the ball would lift just slightly enough so that you could control one axis.
Yeah.
So can you share my screen for a second?
Yeah. Roger's in control. Yeah.
I am exactly like that, but I'm not even missing theory. But as he was speaking, I decided to put in some, I don't know, random numbers. And
continue the simulation. Let's see what happens. Just continue from where it is. Let's see.
I just stopped when I got this stable part.
Nice.
Not bad.
Okay. I have no idea.
Yeah. I mean, you might hit it by luck.
Fully admit it.
Can you reset and run again? I want to see what happens, how the transients look. So hit reset and then run. So let's look at your solution. Okay, not bad. So you yanked the gains all the way up. I think I didn't go above about 20, 25. So clearly I went too low. All right. Yeah, nice.
Okay, I like I said, you're using these words. I don't know exactly what you mean, but if you mean that we were responding too weakly.
Basically, so We had no intuitions because I don't know, the numbers are there, masses of like 1 kg, length of 2 meters or whatever, but without doing the math you don't actually have any calibration of how strongly to push, right? But yeah, higher means higher the numbers you put in, the more strongly the feedback law will react to small perturbations. I mean, it's very simple, right? Like you have a k proportionate at 100, and you can see that, yeah, it's k proportionate times theta. So if theta is, say, 1/10 of a radian, you'll get 10 newtons of force. I assume this is using standard SI units. Whereas
Yeah.
I did 25 maximum, so I would have had 2.5 newtons of force. So it's not the directional intuition is obvious, but the actual numbers, yeah. So you win sort of the
So I admit it. Your luck.
yeah. Let's if you can stop sharing, I'll share the chat GPT and walk you guys through what I had so far. So yeah, I took way back a nonlinear control course that basically walked through a whole series of controllers for the inverted pendulum because it's a very good test bed. Okay, so I'll sort of walk through this rapidly, at least the theory part, then we can take another sort of like break where you guys can look at it yourselves and interrogate it. But yeah, kind of the obvious things is the mass of the cart, mass of the pendulum, length of the pendulum, gravity. In this case, the simplest case, you assume that the way you're controlling it is by pushing the cart horizontally. So this horizontal force is a control input. X is the horizontal direction, theta is the angle. X dot, so derivative of x is the cart velocity, and theta dot, sometimes written as omega, is the angular velocity. And if you do the basic, physics equation solving, you get this equation. And as you can see, it's nonlinear because it's got some linear terms. So x double dot, so that's acceleration, and theta double dot, and those two are linear terms. But cos theta is a nonlinear term. Theta dot square, so that's velocity square, is nonlinear, and sine theta is also nonlinear, right? Pendulum, same thing. X double dot is linear, but cos theta is nonlinear. Again, the L square is fine. Theta double dot, and then another sine theta. And by the way, here, the best way to understand linear, since there's a differential equation, if you remember your Laplace transform theories, if you do the Laplace transform, you'll basically get kind of a linear equation in the S parameters. So that's one way to think of it. Okay, so that's the nonlinear equations. You just have to eyeball it and not really get it. But what you usually do is, this is basically gets strongly nonlinear if theta gets a little big. And you can see that by, if you remember your basic math, if theta is very close to 0, then theta and sine theta are approximately the same. So sine theta becomes like theta. And if cos theta becomes close to 1. So that's the basic approximation. And if you kind of like work through it, you get this equation, which, trust me, is linear. So you get this new pair of equations which are linear. And then what you typically do in designing a controller is you design a vector of all the states you might be interested in controlling. So in this case, it's position, speed, angle, and angle rate, right? So those are the 4 things you might want to control. And the input is the force F. And typically you end up writing this kind of vector equation. So x dot equal to ax plus bu, where x is the vector. And you have this matrix that's called the natural dynamics of the system. The B is the input matrix. And this is, as you can see, this looks like this should look linear to you. So there's a linear differential time invariant equation. And you're assuming that you can observe everything. And the way you capture that is C equal to the identity matrix, which means you can observe all the states. And there's no input passing directly to the output. So if that's there, this D matrix will be non-zero. But for any what's known as a causal system, so cause and effect type system, this has to be 0, because if it's passing right through, it's acausal. So that's kind of the basic setup. If you haven't encountered this stuff before, don't worry about it. This is the equation. If you ever see it, this is the basic linear control model of anything, right? And Usually what you want to do is compute the eigenvalues of this A matrix. So remember, this is an approximate model that only works for small theta about the vertical position, maybe plus or minus 5 degrees. If you looked at the simulation, I think it started off at somewhat like 8 degrees. So it was slightly in a nonlinear regime. But yeah, you linearize about that, and then you check the eigenvalues of this matrix. And again, you may remember if the eigenvalues are negative, you've got a stable system. If they're positive, you've got an unstable system. If it's right on the y-axis, then you've got a marginally stable system. And in this case, as it happens, you've got two, so these are called poles. So you've got 2 poles of the system on the origin. So that's marginally stable. And the other 2 are, one is unstable, so plus and minus. So let's see, what else can we say? And the typical first thing you want to do is ask if the system is controllable at all. And again, I'm just like flashing this at you. You compute this thing called the controllability matrix, which is, multiply the matrices in this order. And then you check the rank of this matrix. If it's full rank, the system is controllable. So these are some technical things you do. Again, just basic awareness. It's also observable in this case trivially.
Can you
Yeah.
you explain why one means the other?
What do you mean one means the other? You mean why the nonlinear
Why
system?
does full why does having a full matrix mean that you have fully controllable? Some intuition.
Let me see if I can think of a good example.
Isn't it because there is coupling? So if there is coupling, we can control. If there is no coupling, so you have a column with zeros or stuff like that?
Yeah. So the technical intuition is you basically get a degenerate system. And the simplest example I've encountered is if you're trying to balance a broomstick on your hand, you can balance it, right? Now, imagine you have 2 broomsticks on your hand. Do you think you can control both of them at once on the same hand, 2 broomsticks? And take a guess. If you have 2 broomsticks on your hand, under what conditions might you be able to control them? This was a question on my undergrad final. So if you've played around with broomsticks, you might understand the intuition behind the answer. But if the broomsticks are of very different lengths, so one is very long and one is very short, then you can control both with one hand. Because what happens is the long broomstick has a slower time constant, the short one has a fast time constant, and you can control one and the other one won't go totally out of control. Get it back into control. Now, if you write the controllability matrix of this, you will notice that it drops rank when the 2 lengths are the same. So you'll get some sort of term where L minus L cancels out and some term drops to 0. So you drop rank in the controllability matrix. That's one illustration of when this kind of thing can happen. But otherwise, honestly, it's like a complicated differential equation result that you derive and then you just blindly apply. I think MATLAB allows you to directly check controllability given A and B, right? So far, we still haven't gotten close to what the Elegoo tumbler is like. Oh, by the way, there's a similar condition for observability. In this case, we're not really worried because we're observing everything directly. But if you can only observe some of the variables, then you can ask, can you reconstruct the whole state based on the ones you can observe? So for example, if you can only observe the angle, you can take a numerical derivative and you can compute the velocity as well, right? So that's an observable system. So that kind of thing. So there's a similar test for that, but let's not worry about that.
So can you put the observability into terms of like what's a real thing? What's observable? What's not?
A good real example of observability. ChatGPT told me that just the Hall effect sensor for a motor's position is not good enough to observe theta because the derivative is not good enough. Let's see what's not. Let me think of it. If I can think of like a very clear, easy example,
Well, the observations are like, these are the sensors that we have available.
So that's the observations. So you want to ask.
If you didn't have an IMU, you wouldn't know something.
Yeah, exactly. So in this case, as you'll see, it'll actually tell us later that without the IMU, you can't actually control this. So that's an example, but it's not intuitive why that's so, and I'm not able to capture it.
Is there an example with an inflatable balloon? You take a balloon, we can measure the size of the balloon, but we cannot measure the pressure. There was an example like that. So we cannot observe the pressure.
Yeah, that might be an example because there's some unknown parameters like the elasticity of the rubber or something. So you can't directly estimate the air pressure without observing or measuring it directly.
Yeah,
So
without a dedicated sensor, basically. Right?
Yeah. So you either have to know the dynamics relating the various variables, which allow you to compute it in a numerical way. So, for example, if you have a position and there's noise in the system and you numerically differentiate it, it'll amplify the noise. So it may not actually be usable, right? So you need both the physics to connect the variables you want to observe, and you want them to be noise-free and computable. So there's like a computability criterion as well. But there's an example, I think, later on. Let's keep going. Okay, so the simplest way you can control these things is, basic static feedback. This is the example you guys played with. So this is, this is in vector matrix form, but this is how you would represent trying to do just position and angle feedback. And as you can see, it's telling you that you cannot place all the poles to stabilize the inverted mode. That's the technical way of saying just position is not enough to control, but you don't have to observe the velocities. You can compute them in this case by computing the derivative numerically. So it says that here. So derivative control isn't necessary as in directly measurement, but you can build an observer to get at it. So if you've heard the term Kalman filter, that's a popular kind of observer. Okay, so I asked it to solve for the stabilizing gain as a function of system parameters. So it did the math. I haven't done this myself in a long time. This is a popular formula you'll find in Controls 101 textbooks. But yeah, you chug through the formula and it gave me closed form answers for the gains. So these are the gains if you want to control on the full state. So if you know positions and velocities of both angle and horizontal position and you plug in these formula, presumably you'll get the stabilizing control. This, again, remember, if you start fairly close to the vertical, if you go too far out, all the assumptions break down since this is linearized about the vertical. Okay. Then I asked it what happens if we are using a torque on wheels via motor as the input rather than horizontal force, right? Horizontal force is you're pushing the cart from the side. Torque is, you're twisting the motor. I haven't actually seen this myself in my old coursework, but apparently the change is not, it's fairly trivial. You move from masses to moments of inertia, and there's some simple multipliers. And yeah, the B matrix changes, it scales via some constants, so not much is happening. If you account for wheel inertia, you kind of have to, I'll have to sit down with pen and paper and figure out what they're doing here. But it claims you can combine rotational inertia and the mass to get something like an effective mass, and that can be plugged in and it'll work. So I'll have to check this. It might be hallucinating this, probably not. This stuff is so standard, I'm sure there's a lot of it in the training data. So then it offered to do motor voltage and current. And here I'm wondering outside stuff I've seen since I've never done the modeling of the electrical dynamics. But yeah, it produced all this stuff. But just glancing high level at the things it thought needed to be modeled. So assuming a DC motor, which I think is correct for our tumbler, there's an efficiency that's straightforward. Wheel radius, no slip condition is fine. If you have a non-slipping wheel, there's a what's called a non-holonomic constraint tying the wheel rotation position to the horizontal position, right? Because if you roll by 2 pi r, you would have gone 360 degrees, right? So the two variables are coupled, but apparently that doesn't matter too much. But yeah, there's some electromechanical stuff going on here. The state space is here. It's apparently, again, nothing much changes, but if you want to include back EMF, that's adding another actual state variable, which kind of makes sense. And in this case, it looks like you can accommodate it by just introducing some damping. You don't need to actually model the potential, looks like. Anyway. But if you want the actual full electrical dynamics, so I guess that means magnetic and electric fields building up and going down, all that stuff, then I think you do have one extra state. Yeah, fifth order plant for joint electromechanical stuff. All right. I'm asking it, does the A matrix change with the torque case? And basically A does not change. The B, how the input comes in. So whether you're pushing the cart or rotating the wheel with the motor, it's basically the same as far as the pendulum is concerned. It experiences a horizontal motion. Let's see. Torque input with wheel inertia. There's some change because now you're doing some, rotational angular momentum stuff. I'll skip this stuff. Back EMF shows up as damping. This is going well beyond what I've ever seen. Motor current, I'll have to work through this and see what it's even talking about. But okay, now we're starting to get a little bit more closer to our LEGO. So I asked it in the two-wheel setup. So basically, think of it as a unicycle. Even though it's two wheels, it's really kind of a unicycle. Okay, I'm asking it if it's any different from the simulator that we just saw, which had four wheels and so forth. And you can glance at the math, but I think, yeah, nothing changes except parameter substitutions and using compound pendulum inertia instead of the a massless rod with a concentrated point mass at the end. That's simpler, but you basically start doing this with moments of inertia instead of forces and masses. Okay, now let's start making it more realistic. I asked it, how should we model yaw? So this is the steering control variable when you're steering it, okay? So I'm telling it, assume it only steers via heading angle, which is basically what the tumbler does. It did the math, small angle, upright linearization, no slip. And yeah, this is getting into stuff I haven't personally done, but it came up with, let's see, the terminology it came up with is, okay, hold on. I missed where it put that. Yeah, so by steering is differential, as we know. You like move the two wheels backward and forward so you can spin in place. Let's see, what is there to say about it? Oh, I didn't know you could expand this and show how it thinks. Okay. Let's see if there's anything worth mentioning here. But the basic thing to know here is that the steering dynamics and the balancing dynamics are basically decoupled. You can kind of like deal with them separately. You can put them all in the same set of equations, but they don't really mess with each other too much. You can kind of see it in the A matrix. You've got this upper left block with a lot of parameters. That's all the balancing dynamics. And I believe this is the steering dynamics on the bottom right. So they're kind of like block structured matrix that's independently controlled. So it's like two different control systems going on.
There's a column of zeros.
There is a column of zeros. Yes, I'll have to look into that. That would normally mean there's something uncontrollable going on. But it may not matter. Maybe that's a variable we don't care about. So this is a concept you might encounter. So when you talk about controllability and observability, that's about the whole state. Sometimes you'll also hear people talking about stabilizability and detectability. So stabilizability is, are all the uncontrollable modes also stable? So you don't care if you can control something that's naturally stable, right? But if it's unstable and can spin out of control, then you do want to control it. So it's okay to have uncontrollable modes if they're also naturally stable. Similarly, there's a notion called detectability. It's okay to not observe a state if it kind of basically goes to zero. It doesn't do anything interesting. But yeah, I haven't dug into this math. I just did this afternoon. But these look like well-behaved equations.
Does the steering take into account the tumbler turns, right?
Yeah.
If you so like how do you compensate for that?
This is assuming what it called a unicycle shell model. So it's approximating it to the case that the two wheels are basically identical and there's some differential torquing and stuff, but you can replace that with a single disc spinning in place. So if you're not turning very rapidly, like you're not trying to like be an ice skater on the ice, it's a reasonable approximation, thinking of it as a unicycle. Let's see. What else? Okay, now I started asking it some other questions, and I won't try to explain the math. You can work through it if you want. But the first case I gave it was what happens if the robot is on a slope? And here it basically validated my intuition that the pendulum will still be along the gravity vertical, but relative to the body of the robot, it'll be kind of leaning forward. That's the statically stable situation. And it does it by like projecting the gravity vector in the two directions and like treating one as a bias and the other as weakened gravity, something like that is what's going on here. But of course, as you might imagine, if you're standing on a slope, you have to put in a constant motor torque to just stay in place. But there's no extra torque required to keep the pendulum vertical. That's the basic idea here. Let's see. And these equations apparently are, I asked it later, it's not in the link I shared, but I was asking it more questions. But it's any orientation on the slope. So it could be heading directly uphill or it could be heading laterally. So it's like leaning to one side on the roll axis. So it sort of takes into account these things. But it's got the terminology a little bit messy, but it looks right to me. Oh, on a slope, it's basically the same equations as before, unless you're trying to turn on a slope, which makes sense, right? Because one wheel will be riding up, the other wheel will be going downhill. You'll get like rotational moments as well. Let's see what, okay. Then I asked it about a constant headwind or tailwind. Again, nothing much is going on. You can kind of imagine what happens, right? You lean into the wind. If you're like trying to walk into the wind, you kind of lean in to compensate for being pushed the other way. So that's basically what it'll do, this solution. Again, you're linearizing.
You can also,
Yep.
you mentioned wind. So you also can talk about what wind profile will make it uncontrollable.
Wind, if it's steady and you have enough control authority, so the controls, so all this is assuming you have enough control authority, so the more actuators do not saturate. Steady wind within control limits is basically manageable because you basically ramp up the integral control term and compensate for it and push back steadily, basically. So unless the wind is too strong, then you get blown over completely. The most interesting case is asymmetrical loading. So this is interesting for us because if we design a little manipulator to put on the robot so that it extends, picks up an object, comes back in, that's basically fairly complex. Now, the intuition I want to convey here is think about how you do it. We are all inverted pendulums walking on our feet, so slightly different actuation, but we are inverted pendulums. If you pick up a heavy box, the way you balance is you lean back so that the net center of mass still passes right through your feet, right? So that's how you intuitively do it. Basically, this solution will do the same thing. So if it picks up something with a manipulator arm facing forward, it'll lean back to bring the center of gravity above the wheelbase. So this basically formalizes that solution.
So does that imply that like the same model, the same control system that you would build to work without that wouldn't work with it?
You will still have to accommodate it. The same structural model will work, but you might have to like, substitute the parameters with some effective loading. Instead of like the literal length of the pendulum, you might have to compute the new center of mass and like put the virtual line connecting it, things like that. So there's some control strategies for that stuff, but the basic dynamics don't change that much. it'll just, the conceptual robot will start drifting from the geometry of the physical robot. So, the vertical equilibrium balancing point will not look like standing up straight, that kind of thing.
And generally something as simple as like a pin controller would be trying to get it to stand up straight. It wouldn't be stable at a weight back.
I mean, a naive, if you just had a PID controller tuned for the nominal vertical, and then you just randomly added a manipulator arm and loaded it with a small load, that would just fall over because it has the wrong assumptions about the world. It does not know that the center of mass is shifted. But if you accommodate that, redo the parameters and plug in the right modified parameters and recompute the PID gains and plug them in, then it should be able to balance, because now you'll have altered its worldview. It no longer thinks vertical is the same as the physical rod of the pendulum. It might now think vertical is off by some degrees, right? But generally at this point, you want to start moving away from completely naive PID controller and start doing somewhat more sophisticated things. So Eligu, by the way,
is there a way to autonomously detect?
Yes, there is, and it's there later in the chat. So you have to start doing a little bit adaptive control at that point. Let's see what else is worth talking about here. Headwind, tailwind. I asked it some questions about it. Fore-aft asymmetrical load. By the way, this model accounts for both the idea of a manipulator arm sticking out forward and picking stuff up, and what we already have, which is the asymmetric tail on one side, which we've added the little caster to. So that's already an asymmetric load. Think of it as like a fixed arm that carries a fixed load, which is the caster wheel. It's fairly low down, whereas a manipulator arm would be higher up, but it's the same kind of model accommodations that are needed. So just to look ahead a little bit, I believe we should be able to rewrite the controller to do balancing even with the asymmetrical loading of the tail and the wheel. So it should be able to balance even then by sort of leaning back a little, basically. Let's see, what else is worth looking at here? Slope keys. I tried to make it draw some diagrams. It sucked, so I gave up that. So don't try to read these diagrams. They're terrible. All right, let's see.
How long did all of these discussions with chat take you?
This was a couple of hours. This is all stuff I remember doing 25 years ago. So mostly it was like scraping rust off what I've done before. And it's been like 20 years since I touched equations like this. But eyeballing it, it looked all reasonable. It didn't look hallucinated. So I think this is, and I don't think it looked up much. So I think this is all in the training data, because I think it's in so many textbooks and like online homework problem sets. It knows this stuff better than we do. But okay, yeah. So I asked it some stuff. It's got its notation a little messed up, and coordinate systems, don't trust them too much, but the basic math is right. Let's see. So this, I think at this point, I asked it from some. Okay, so now we start doing some more complicated things. So far, we've made the assumption that we are linearizing the controller and working near the vertical. And usually when you do that kind of linearization, you do something called estimating the region of attraction. So there's like a systematic ways to do this using the eigenvalues. Usually the intuition is for inverted pendulum, it's no more than a few degrees. At that point, PID type controllers will fail. And you can see that with the tumbler, right? It can, if it falls over on the non-tail side, it can't pick itself up again. On the other side, if it's stopped by the tail, you'll notice it does like a jerky motion to get back on. I suspect it does something nonlinear in the initial getting up portion. I haven't yet looked at the code. But yeah, region of attraction, it came up with like some basic calibration, some really yucky math. So region of attraction math is like really yucky. It's not very elegant stuff, but you can kind of do it. But this is just to give you an idea that we do this sort of thing. Okay, now I started asking it about more complex controllers. So the first kind of like more advanced controller that's worth us maybe thinking about. So I might try to implement this if I can get into the code and get good enough at the implementation side. There's a type of control called feedback linearization, where you basically artificially make the nonlinear equations look linear. And the advantage is this gives you a much larger region of attraction than small angle, like, naive linear control. And as it shows you, it gives you like 60 to 80 degrees. Limited by how strong your actuators are. We had to do this in my nonlinear controls class. This was one of the homework assignments, and I remember it was a lot of fun. Like, we had been tuning the linear controllers, and it was like very annoying to see it collapse after just 5 degrees. And then the professor taught us this, and coding this up, it felt like a huge achievement that now the thing could balance with like a 60 to 80 degrees range. But basically, yeah, you can look through the math. The intuition is you try to make the nonlinearities kind of like look virtually linear, because they're kind of well-behaved nonlinearities. Think of it that way. And it gives you one solution. It's not trivial stuff, but I think this is reasonably computable. I asked it, what is the intuition behind feedback linearization? And it gave some answers, which you guys can look at if you want to. What else did I ask? Okay, then I started asking. Oh yeah, let's see what else to. Okay, never mind. Okay, then I asked it about controlling motion in the plane, and this is the architecture it's set up, which is, I think, the way it's done. The outer loop is the unicycle, inner loop is the balancer. The inner loop is very fast. I'll show you some numbers later, but outer loop is slow. There's a way to set this up using arc length parameterization, which you may have seen if you've seen any differential geometry. But think of the variable as the distance along the curving path that you're traveling, and then you use sine and cos to compute the velocity vector, and then you integrate the velocity vector to see how far you've gone. So that's kind of how you do trajectory following. And it has like a basic architecture. Again, I've seen this sort of thing before. It looks right, eyeballing it. And yeah, this is an important principle. You kind of want to make the inner loop faster than the outer loop. So this is not quite controllability in the linear case that I showed you, but it's the same kind of principle. You want to separate dynamics to have different time constants so that you can control both at the same time with the same actuator. I asked it a little bit about observability, and it says Hall effect alone is not enough. So yeah, it says minimum body IMU is required along with an observer. All right, this is where I switched to, I just gave it all the code. I think this is the right version, and asked it to start helping me think about applying this theory to implementation. So let's stop. Like,
does it unzip also the?
Yeah, it unzips. It looks through everything. So yeah, before we dive into the code and like try and get a sense of it, why don't we take another 5-6 minutes for you guys to scroll through and at least get a feel for the math, like, just intuitions about how the variables are named, what the equation structure looks like, that kind of thing. Just basic familiarization. If you loaded up the chat, you should be able to ask it questions about anything except the code, because I think when you share a ChatGPT link, it shares everything but not uploaded stuff. So if you want to ask it questions about the code, you'll have to upload the zip into your session as well, I think. And I shared the link of the Tumblr code.
So which chat is this? I see some mission planning.
The very first one. I have 3 chats. I posted 3 chat links. The top one, the inverted pendulum one. It's in the thread.
Wild Road.
What?
It takes it a while to load.
Yeah, it is a long chat with a lot of LaTeX math in it, I guess.
Yeah, I couldn't get it to load in Safari, but in Firefox or in Chrome it is. Well, it's not rendering it as nice as yours.
Wait, I don't see the. Oh, okay.
Yeah. Where is this? I don't see this car initialize and stuff.
It's in the middle somewhere.
Ah, okay.
Okay, can you ask the system how sensitive it is if we changed it from 5 milliseconds to 10 milliseconds? What effect that would have?
Oh, for that, you need to have like the actual model of the specific system you're trying to build and just actually do the math. This chat won't be able to tell you because I haven't given it any actual numerical parameters. And the Elegoo code does not contain any parameters except the controller gains. So that's kind of annoying. We're going to have to do some measurements to figure out, masses and inertias and crap like that. Unless it's buried somewhere in the documentation. But yeah, all that standard kinds of analysis, sensitivity analysis, transient peaks, all that stuff is tedious standard control design analysis.
Can we trust him? Is there any way of checking for people who don't know control theory?
You'd have to simulate the system and see if it behaves as ChatGPT predicts, or you have to go verify the math yourself. So I'm like eyeball level trusting what it's given me because it looks like what I remember seeing 30 years ago. But my to-do item is to go sit in a coffee shop with an iPad with this screen on, and then actually follow the math and like verify it and make sure it didn't like screw up badly. But beyond that, yeah, you have to like basically load this model into a simulator and actually try to, if it claims that the gains it computed are a stabilizing pollution and it does not stabilize the robot, it's wrong, right? All right, let's take a couple more minutes.
Well, what's special about chat is that it specializes in giving things that look plausible, but might not be. So eyeballing it won't do it.
I think this one is probably reliable because this is ChatGPT 5 in thinking mode, and I'm hearing people saying it's solving like really difficult math problems. And also, I think another reason to trust it is this is extremely well-known stuff that has a lot of like training data on it. We're not asking it to do novel stuff.
I don't know.
But yeah, I mean, we have to try it out.
There's nothing in between eyeballing and actually trying it out, simulating.
Not really.
How would you get the inertias? Sorry.
I just said I wanted to say I want to believe, okay, but how do I?
Can we ask it to generate some kind of test suite or whatever that we could run offline?
So I think that's best to do in a slightly more restricted, different chat based on the Tumblr code. Let's actually, yeah. If you guys are done like poking around at it, we can continue walking through the rest of the chat, and you'll see if I've covered the kinds of things you guys want to talk about. I tried my best to cover some of it, but okay. Let's see, how are we doing on time?
You have the
8 minutes left, so let's not look at the code, but let's go past the code. I'll show you what else I was asking it. So all this unpacks like how this kind of theory is implemented in the off-the-shelf Elegoo code. And yeah, the main files to look at, it says are Kalman filter, the two files called that. Then there is there's a balance card. Where is this? Hold on. Yeah. Somewhere it had a list of things worth looking at. Yeah, there's a balance car.h. There's two Kalman filter files. There's one that seems to be about the processor, and then a command, which is the outer supervisory loop. Yeah, and then I had it walk me through some of these files. But this basically explains how the balancing stack actually works. It looks like a basic PD controller with an observer on the IMU angle reading. It works as the theory you would expect, but it's fairly naive. It doesn't do any more sophisticated stuff. Let's see.
So it says that the firmware doesn't have any masses and inertia. So masses we can calculate, but like how would you?
Masses we can calculate, then we can sort of roughly sketch the geometry and measure the moment arms and figure it out. Or we can like build a detailed CAD model in a CAD software, and those things can figure out all those things, like center of mass and moments and stuff. But you actually kind of don't need that. And I was asking it about how to define control strategies that get beyond that. So let's see what else. Oh yeah, this is the specifics of the LEGU1 represented in the theoretical math form. So yeah, it basically mapped the old equations, came up with some numbers, what it could infer, how it maps to theory. What else? Okay, so then I asked it, give me strategies for improving the control code. First thing I asked was, can we replace the small angle proportional derivative controller with a feedback linearized or gain schedule controller? So this is kind of what you were talking about, Anuraj, for your satellite. So in this case, it would give us a much larger angle of recovery. So this is one big workout, basically, and it gives me ideas of where in the code to start working on it. Then I asked it about the manipulator arm, and yeah, it gives a strategy for like doing that. And here it does some of the things you were asking about, Anuraj, which is like, you don't have to measure the load you're picking up. You can pick it up and then like shake your hand a little bit to get a feel for how much load you're carrying, and use that to estimate your changed inertias. So you can do very simple adaptation strategies here. Let's see what else. Feed forward knowledge. So if at the top level above the inner and outer loops, you kind of know what plan you're following. So suppose you've come up with open loop commands like move forward 1 meter, extend your arm, pick up the tennis ball, and then retract the arm, and you have like time stamps and all that. That's information you can use. And I was asking it, how can you use that feed forward knowledge of the mission plan to actually modify the control? And should we do it or let it figure it out? And it suggests to do both, like use the feed forward, but also let the inner loops adapt continuously. So that's basically what's called hybrid control. Let's see. Okay, so this is where it got really complex. So I asked it to design a switched mode controller, which basically is, we want the energy efficient 3-wheeled mode for like normal running around, but it's kind of like not very agile or fast. And when we want to be agile and like spin around and do acrobatic things, then we switch to balancing mode. And it came up with a fairly good architecture of this that I'll have to sit down and evaluate. But basically, I think what we can do is within the LEGU, we can have it be basically default a 3-wheeler, and then sometimes switch to 2-wheeler and do agile things. And the main advantage is a 2-wheel inverted pendulum robot is not actually a very good form factor for a rover, because the inner loop is fast time constant, which means the motors have to be constantly on controlling it. So it's kind of like a energy hungry as well as like a fast moving type of robot. It's meant for like high speed and high energy sprinting basically. And roving is like a slow energy conserving mode, right? I think doing both basically gives you a new kind of rover. So unlike our 6-wheelers and other like Mars rover type things, this gives us a rover that can sometimes do very slow tortoise style energy conserving roving, but other times it can like basically start sprinting. Like, maybe there's a volcano that's exploding and it needs to run away fast. I don't know. But it seems like an interesting thing to try. But yeah, so this is my conversation about that. And again, eyeballing it, it looks reasonable. It even came up with some numbers and stuff. And then finally, I asked it to suggest a roadmap for implementing it, all this stuff with the Elegoo code. And it came up with something. So we need to dig in and see how feasible all this is. But again, eyeballing it, it does not look hallucinations or weird.
Didn't ask, just give me the zip file so we load it up.
I think we'll get to seriously close to just vibe coding this whole roadmap in like 6 months. Right now, I don't think it can vibe code this. But let me see. I shared 2 other chats that you might want to look at leisure. But let's see. One of them is what. So one I was
looking at this headless mission mode.
Yeah, so there right now it's all interactive with the phone app, which is a very annoying configuration. So I was asking it basically, how should we design this so that we can push a button in the app and it switches to an autonomous control module that does something simple, like, run around in circles or do a random walk or use the ultrasonic sensor to do obstacle avoidance, but then in an increasing radius, do a search pattern and just map out the entire region it's roving in. So you can have a bunch of simple canned missions that don't require any interaction. And maybe you can just tell it to go do that. And the architecture I was suggesting to it is, especially if we have the ESP32, so you don't need to be tethered, you should be able to switch from headless autonomous mode to interactive app controlled mode. But there should also be 2 other modes, which would be basically safe and ready, and the other would be kill switch. So a button with a GPIO that you hit and then everything shuts down in a safe state. So that was one chat. And the third chat, I just gave it all the details of the project state and everything we are trying to do, and asked it to come up with kind of more of a project plan. I think this is good enough now that we can use ChatGPT as our project manager.
I looked into that headless mission because it was talking about something called like a compact script for the mission states.
Yeah.
So like there's something called Xtext. It's a domain specific language creator. It's a Eclipse Foundation project. So it will give you the entire framework for like a compiler linker, and you just have to define the grammar of the language, and then it will also create the parser for it, the compiler for it, the linker for it. So you basically it's an infrastructure to create domain specific language.
I think that's the direction it started going off. Like when I first told it look for headless, it seemed to go very low level. Like it was making up opcodes and stuff at that level, and I then told it to back up and do it slightly differently. And I was telling it, design the headless mode as a top level abstraction. So the low level stuff will be the inner and outer loops we just saw, and this would be something more like the language Rhett was trying to design. Like have the composable primitives in close to natural language, like forward, backwards, similar to the Farcaster command language, and then missions would be defined in those terms. So I think those are 2 distinctly different approaches. You either put the headless mission controller on top of the stack, or you put it at the bottom of the stack. And I'll have to think about maybe this can be another session and we can walk through the chat and discuss it next time. Anyway, so hopefully that was a useful random dive into the basic dynamics of the robot. And I think this is enough support that even with my very rusty abilities, I might be able to like actually do some progress along this path with ChatGPT's help. Like left to myself, my technical knowledge is way too rusty to do it by myself. But with ChatGPT, I think I can maybe do some stuff. So I think if you look at the roadmap in the third chat, I suspect we can do something like fiddle with the basic balancing code in the off-the-shelf tumbler configuration, and like figure that out and see what we can do there. And in the meantime, you can in parallel try to port it to ESP32. There doesn't seem to be very strong coupling between those two. So you can work on the control subsystem and the ESP32 migration in parallel. There may be a few coupling points, but other than that, it looks like these can be two parallel paths on the project.
Yeah, thank you. It's very cool because for me, likewise, yeah, I think I've studied about most of it, but it's a very long chat. Okay, so I read until maybe the middle. Okay, and after it, lack of time, but it goes pretty far away. So obviously we need to check whether it's really working. But as a guideline, okay, like as a map of what we want to look look at. Okay, it's very interesting and very supportive, I believe. Even if it's not correct, at least we have a vector, okay, where to look at, and so it's a bit to also to reply to Meyer earlier, is that between that and definitive answer, there are several steps definitely. But at least right now, it's not a random search anymore. Okay, we have a kind of good idea of what the next step is. We have a Markov process in the making.
And I was thinking about that middle ground that Mayor was talking about, and I started on this but didn't have time to get far. The WeBot thing that you showed, I actually asked ChatGPT what are the good simulators, and it came up with the ones we've looked at, like Coppelia and the others. But it said the simplest to start with is probably WeBot. And I asked it, like, what would it take to import some of these basic control models into WeBot? And it gave me the beginnings of a strategy. So I'll do that the next time I have a chunk of time to work on this. I'll try to come up with the simplest two-wheeler model that we can load up into WeBot, and that'll be a simple place to test some of this stuff, right? Because actually putting it into the hardware code of the tumbler is a lot more involved. I think we can like do proof of concept in the simulation first.
There is perhaps a nice synergy here because now for a few weeks, since I have my own tumbler, I have used ChatGPT 5, to try to generate a 3D model. Okay, so using URDF and SDF and such kind of formats used in robotics and supported by Webot, Gazebo, ISAC, and so on. It didn't go well, okay, but I ended up actually using OpenSCAD, and so I have actually a hand-drawn model, okay, where I separated the wheels and the motors, and after just the shape is actually is available, okay, and it's on OpenSCAD text file. I'd be curious if we can feed that as an input to see whether it can help speed up towards generating a controller for Webot.
Yeah. If off-the-shelf model is available and it fits the equations, we can use it to test control stuff. But yeah, the model does have to represent things in the way that you can say, apply this voltage torque here, that kind of stuff. So it has to be instrumented for the right purpose. Let me try and get started on WeBot and see if we can get a simulation track going, because I think that's the right level to start. But in the meantime, I'll also start poking around at the code, like at least at the very basic. I bought another tumbler since we are using one to mess around with the ESP. So I have one unmodified tumbler. I'll start simple experiments with that, like maybe just flashing it with different controller gains and getting some feel for how to modify it. So that should be fine, right? Just take the code and reflash it without changing anything except small bits of the control code. So I think those are the two things worth trying: build a simulator model of the tumbler and start tweaking the balancing code a little. I think my end goal for the control track would be to get to the two mode control of like three wheel versus two wheel operating modes, and the ability to uh, hold unbalanced load. So small manipulator arm that picks up stuff. Those are, I think, two good milestones to shoot for.
Do you think it's possible to close the loops through ChatGPT?
I
Is it
haven't
still
experimented with
search
the agentic
resolution
stuff.
space?
There are people who've done this stuff, like, give it all the access to GitHub and stuff. It manages and runs the code, checks it in. I don't know if it can handle flashing the robot and closing the loop. That may be far away, but I think you can get.
Oh, it needs to view the robot and figure if it's falling or not.
That's, I think, too far. Like, it's an order of magnitude worse than having it do CAD like Eric was doing. So a friend of mine, he was the guy who came up with the wipe CADing phrase. So he was trying to do this. He made it wipe CAD a very simple 3D print, and then the print went horribly wrong when he was running it overnight. So his next project is have a camera looking at the 3D printer as it's printing, and just like flag an alert if the print goes wrong and turn it off. So,
But there are projects for that already.
there's what?
It's there is a project called Octoprint or something. So you can basically attach a camera to a Raspberry Pi, and then it does something like this already.
And this is a simple control loop, right? Like, you check for things wrong and turn it off. That's the simplest 3D printing control loop. If you want to do something similar with like iterating the robot control algorithms, you have to do stuff like, all right, update the controller, flash it on the robot, turn the robot on, watch what it does with the camera, interpret what's going wrong, and redo the controller and try again, right? So that's the full iteration loop. I think
Yeah.
that's too hard if you want hardware in the loop, but it may be doable with like Weibo in the loop, like, because the simulator model is both simpler, and I think it'll output full log files, right? It'll give you the full history of like x and theta and the variables you need, and maybe it can analyze with that. I don't know, but I think that's second stage tooling. I think right now we kind of have to do more basic things. All right. Thank you all. Hopefully we'll
Thank
do
you.
something with this.
See you later.
Thank you. Good night. Good day. Great.